Now that we understand what a density curve is, we're going to focus on a very particular type of density curve. That curve is called the normal curve, and this is normal with a capital N. Not just to be quirky, but normal here means something different. Normal curves are a special type of density curve. Let's talk about, the shape, the center, the variability of these curves. All normal curves have the same overall shape. They are symmetric, they are single-peaked, and they are bell-shaped. Now remember, we're talking about the density curve here, not like a histogram. The center, the mean, mu, is located at the midpoint of a symmetric density curve. It's also going to be the same value as the median. And talking about our variability, the standard deviation measures the variability, also known as the width of a normal distribution. We're going to be using mean and standard deviation as opposed to other measures of center and variability because of the symmetric nature and the special properties of this normal curve. As far as the notation, you can shorthand if you know something is a normal distribution with a capital N and then in parentheses the mean and the standard deviation. If you have a normal curve, you can find your standard deviation by finding the inflection point. In mathematics and statistics, the inflection point is going to be the point where the curvature changes. If you've taken calculus, this should be a review concept. When you're looking at a curve, think of it, you're going downhill. From here to here, look, your curve is kind of going down like a frown. And then even though your curve is still decreasing, the curvature is now curved up like a cup. So that point where it changes from curving down to curving up, that is your inflection point, and that is the distance of one standard deviation from that apex at the top. If you struggle with knowing how to, give a good sketch of a normal curve, there is some tips in your notes there. You can see here there are two different normal curves. When you have a smaller height of your normal curve, it's going to be more spread out between your mean and one standard deviation. But here you can see how it's smaller. Fun fact, there's more information about this in your textbook. Before the euro was the official currency of Germany, there was a mathematician who was known as being responsible for using the normal curve. He and a picture of the normal curve were featured on the $10 or the 10 Deutsch mark bill. I believe he used normal distributions when talking about errors that astronomers were making. But feel free to do a little bit more research on him. He's really interesting. So why are these so important? Oh, well, great question. I'd love to tell you. Normal distributions are good descriptions of real data, like real life things. So like scores on tests that are taken by like many people. Repeated careful measurements of the same quantity. Characteristics of biological populations. Another, it's also good approximations to the results of chance outcomes. So like flipping a coin and recording the, number or the proportion of heads. Also, many statistical inference procedures are based on normal distributions. So we will see normal distributions a lot in this course, specifically chapters 8 through 12. So they're going to be something we see a lot. All right, we're going to love this. This is called the empirical rule, also known as the 68, 95, 99.7 rule. For any normal distribution that has a mean of mu and a standard deviation of sigma, we know that these three things are true. Approximately 68% of the observations are within one standard deviation of the mean. Approximately 95% of the observations are within two standard deviations of the mean. And approximately 99.7% of the observations are within three standard deviations of the mean. So you can see that visual down here. You're going to get these numbers really ingrained in your head. 68, 95, 99.7. Now, this empirical rule is only true for normal distributions. If your distribution is not normal, or if you don't know what the shape of the distribution is, you can use something else called Chebyshev's rule. This is not an AP topic, so you don't need to spend too much time on it, but if you want to learn more about it, there's some information in your textbook on page 119. Let's see how we put this into practice. Well, here's another visual. So you can see within one standard deviation, so on one side or the other, 68% of your data. The distribution of Iowa test of basic skills, also known as the ITBS vocabulary scores for 7th grade students in Gary, Indiana, is close to normal. So they told me that. That's what I need to know. Here's the distribution. Remember this notation? That means the mean is 6.84 and the standard deviation is 1.55. The range is between 0 and 12. First things first, we want to do a sketch of our normal density curve for this distribution. So when I do that sketch, here are the things I include. In the middle, I need to put the mean. And then counting by 1.55, I'm going to put 3 tick marks to the right and 3 tick marks to the left and put the numbers there based on the calculations. Also notice how I have a label down here on my horizontal axis so I know what the data represents. Then I have my curve, and you can see how my curvature is changing from down like a frown to up like a cup at this 1 standard deviation away mark. Okay? You don't necessarily have to draw this horizontal thing here, the dotted line, but if it helps you when you're sketching your curve, you can. Using the empirical rule, what percent of the vocabulary scores are less than 3.74? So looking at our initial drawing, we can see 3.74 is exactly 2 standard deviations, or the z-score would be -2, 2 standard deviations below the mean. Because it's an exact, we can use the empirical rule. The empirical rule only works if it's exactly 1, 2, or 3 standard deviations away from your mean. So looking at that sketch, we want to shade in the area we're interested in, or what percentage. So less than would be to the left, and you can see that shaded in green. We know from the empirical rule that about 95% of the scores are within 2 standard deviations of the mean. That's what this red shading is. So if you did 100% minus 95%, you would get 5% are outside of that interval. So 5% on this tail and this tail. But we're only interested in a single tail. So the math there is going to be 5% divided by 2, and that gives you 2.5%. Let's look at another example of the empirical rule. Using the empirical rule, what percent of the scores are between 5.29 and 9.94? All right, here is our sketch again. You want to sketch it out. We know that 68% of the scores are within 1 standard deviation, and that 95% of the scores are within 2. And we're only interested in this shading here from 5.29 to 9.94. So we already know that there's 68%. Okay. And then we need to figure out what percent is within this little piece right here. So we subtracted 95%, which represents from 9.94 to 3.74, and divided that in half. So this little interval right here is 13.5%. So it looks like I don't have the actual answer here, but we can do that math really quick. You would just need to add 68 to 13.5, and that answer would be, what's that going to be? Oh, I'm sure you're faster than me at the math, and that's going to be 71.5%. I think that's right. If I'm not right, tell me in class tomorrow. All right, let's have you give it a try. According to the CDC, the heights of 12-year-old girls, 12-year-old males are approximately normally distributed, mean of 149, standard deviation of 9. Sketch this distribution, labeling the mean, and 1, 2, and 3 standard deviations. And then answer these 2 questions using your empirical rule. We'll go over those answers tomorrow. Now, the importance of standardizing. We learned in the previous section about standardizing by finding z-scores. There are infinitely many different normal distributions, all with unique standard deviations and means. So in order to more effectively compare different normal distributions, we standardize. We saw that example in the previous section. We were comparing 2 people's heights of different genders and ages. By finding their z-scores, we could see how they compared. So we can compare apples to apples as opposed to apples to oranges. So for example, we can compare SAT and ACT scores if we standardized. All normal distributions are the same if we measure in size of sigma from the mean mu as the center. Now, the standard normal distribution is just a normal distribution that has a mean of 0 and a standard deviation of 1. So every standard normal distribution has the same look as this normal curve, except the numbers down here are always 0 in the middle, and then 1, 2, 3, and negative 1, 2, 3. As opposed to, if you look at previous examples, we used numbers that were more pertinent to that example. Standardizing the scores of a normal distribution means that the z-scores will have a standard normal distribution. Okay? Standardizing the scores of a distribution does not change the shape of the distribution. So if I had some non-standardized normal distribution and then I converted all of them through z-scores, which we saw in a practice worksheet we did in class, you see now that my mean is 0 and my x value of my data set or of my distance has turned into a z-score. Looking at that vocabulary example from earlier, we saw the mean was 6.84 with a standard deviation of 1.55. If you standardize it all, it turns into this. Okay. To find proportions, if they are not exactly 1, 2, or 3 standard deviations from the mean. So you can only use the empirical rule when it's exactly 1, 2, or 3 from the mean. If you can't do that, you're going to have to use either technology or the table A that's provided to you. Okay. That gives you a table of areas. I always joke that Beyonce made this table because all the areas are to the left, to the left. The entry in the table is going to be your z-score. Okay, and it tells you the proportion of the data. Other values we use, we can say p-value, we can say probability, we say percentage, proportion. Those are all kind of synonymous here. So let's do a quick example. We want to find the proportion of observations that are less than 0.81 in a standard normal distribution. So you want to first sketch out your picture. Okay. So 0.81 is to the right of 0 because it's positive. And if we want less than, we would shade this left-hand part. Then I would look in my table. The way you read your table is up at the top is that going across the top, those are your hundredths place, and then down the side is your tenths place. So if my z-score was 0.81, I would look for 0.8 and then go over to 0.01 and see where they match. So the answer here is 0.7910. What if you were trying to do this and it wasn't already in standard normal form? So if you're trying to find area for any normal distribution, even if it's not already standardized, here's what you're going to do. First things first, you're going to draw a normal distribution, right? Labeling all the things, including doing the shading of interest and noting your boundary values. Then you're going to do your calculations, right? This is showing your work. There are two options. You do not have to do both. I will show you how to do both, but you just have to do one of them. First, you either need to standardize the boundary value, right, by finding the z-score, and then use either table A or technology to find the area under the curve. Or if you want to skip that step, you can just use technology to find the desired area without standardizing first. And then finally, just make sure you answer the question that was asked. Good sentence here is helpful. So again, quick understanding if we're trying to find values in that table A. Like I said, the rows are the ones and the tenths digits, and then the column headers are the hundredths digits. So if you wanted to find the p-value, or the percentage of the proportion, of a z-score of negative 2.33, I would look on the side that's negative 2.3 and go over so it meets with a 0.03, and that answer is 0.0099. If you're just doing this in a calculator, what you need to do, get out your TI-84s or whatever you have, and you go to second vars, it's the distribution button. Pick the option that says normal CDF, and you're going to enter in these 4 numbers, right? So this is for to the left, for instance. So you'd enter in a very small number for the lower number, your z-score for the upper number, and then 0 and 1 for the mean and the standard deviation. Now, if you want to do greater than or for in between, you would see how you'd enter those here. Okay. Quick example, and then I'm going to continue actually in the next part of this video, and we'll walk it through nice and slow.